So in our next section for BGP, we're going to talk about NLRI origination, or network layer reachability information. And specifically, first off, what is NLRI? What are the different ways that we can actually originate it into BGP? So what's the difference between the network statement versus redistribution, some of the other methods. We'll talk about how conditional advertisement works, and then how also conditional route injection works. Now, first and foremost, BGP NLRI, or just NLRI in general, means network layer reachability information, or in other words, just a fancy term for a route. Now, we saw up to this point that there are key differences in BGP about how it does its advertisements versus IGP. And the big difference is that BGP does not know information about the path. BGP only knows information about the prefix. Now, specifically, the way that BGP advertises the information is going to be with two messages. We're going to take a look at the packet captures, which are the updates and the withdraws. So a withdraw is basically a negative update, which is saying to remove the information from the topology. And then the update is where we're actually telling the other neighbors, this is the prefix, these are the attributes, and this is the next top value that's associated with it. Now, as I mentioned, the NLRI origination can be done multiple ways. First and foremost is going to be the network statement. Now, we talked about this previously a little bit. What's the difference between the network statement in IGP versus BGP? Where in the case of IGP, it means to enable the process on the interface. So turn OSPF area 0 on gig 1.5, or turn EIGRP AS100 on this particular link. In the case of BGP, this actually means to advertise a route. And the reason that there is a difference here is that the network does not need to be directly connected to you. So as long as there is a match in the routing table, and this must be an exact match, then BGP can originate the prefix. So as we saw in some previous examples, there's multiple ways to do this, where you could go to every router in the core of the network and issue the network statements, or you could go to just the BGP routers on the edge and then issue the network statement. Really just depends on, do you want a central point of control, or do you want to distribute the operations between multiple devices? In most practical cases, I would say that you should originate the networks on the edge, just because it makes it easier from an administration point of view. We also have three other methods. Of course, we have redistribution, so we can take OSPF and redistribute it into BGP or connect it into BGP. One of the caveats with this is that it does not include OSPF external routes. And we'll talk about this a little bit more detail later, the reason why it does not. It's basically an automatic loop prevention mechanism. And then we have two other methods. One of them is aggregation, and then one of them is the BGP conditional route injection. Now, aggregation we're going to spend a bunch of time on later, because it's much, much more detailed than it is in the other protocols. There's all sorts of different ways to do aggregation. There's all sorts of different attributes that go along with it. So we'll have a separate section that is for that. But the key point for origination with an aggregate, the difference between the network statement and the aggregate address statement is that the aggregate requires one subnet to be in the BGP table, where the network statement requires it to be in the RIB, in the routing table. Now, you can normally assume that if the route is in the BGP table, it's probably in the routing table, but not always. So we would only be able to originate an aggregate if we do have a subnet that is a best route from the BGP best path selection. So again, we'll talk about aggregation in much more detail later, but it is important to know that there's a distinction here between the network statement matching the RIB and the aggregate address statement matching the BGP RIB. Now, specifically with the network statement, when we originate a prefix, we're going to send it into BGP with an origin code of IGP. We'll see that this origin code is then used as part of the best path selection in order to prefer routes that were originated with the network statement versus redistribution. Also, the network statement again requires an exact match in the RIB. So again, it does not have to be connected. It can be learned via IGP, or it could be configured statically, but it has to be an exact match. So if you are issuing the network statement without the mask keyword, the process is going to assume you mean a classful mask. It's not the same as in IGP, where you can say network 10 under EIGRP, and then it takes all interfaces that start with 10 and starts running the process on them. So in general, you must do an exact match in order to originate the prefixes. The other key point here is that it originates the prefix with a weight of 32,768 in order to try to prefer its own origination versus somebody else's. So let's go ahead and take a look at this on the CLI, and let's look at, first off, what is the current state of the network. So now we have BGP pre-configured in a number of different ASs, and we'll talk about the details here of how the peerings are set up later. We're basically looking at just the origination of prefixes for now. So let's say, for example, that on router 4, we're going to do some packet captures on these different links, and we're going to originate some prefixes and then look at what's the differences between them. So let's start on router 4 here, and the first thing I need to do is get my connection to my Wireshark machine, which is on gig 1, and the VM here is in the 10 network, so I'm going to say 10.0.0.4, and then I should be able to ping 10.0.0.100, which I can, and then let's go ahead and do a capture. Now, we already know what the transport profile is of BGP, that it's TCP port 179. So I'm going to limit the capture to that just to make it a little bit clearer in the output what we're talking about. Now, remember that we don't necessarily know in advance who is the TCP client and who is the TCP server. So when I'm matching the flows here, I'm going to do it in both directions. So let's say IP access list extended BGP. We're going to permit TCP any equal to 179, which is BGP, and then permit any equal to 179 any, so both directions. Okay, then I'm going to create the capture, so let's say monitor capture 1, where the access list is the BGP ACL, and then the interfaces, I'm just going to do this on all 3 of these, so let's say interface gig 1.146 in both directions, gig 1.45 in both directions, and then that bottom interface, that's actually the tunnel, the DMVPN tunnel. It's not the underlay interface. Okay, then let's start the capture, and let's look at the show monitor capture 1 buffer. Okay, we should see that we start to capture some packets. Okay, next let's look at the show run section BGP, and we see that we have some BGP peers configured, but right now we're not originating any networks directly. So let's say on router 4, let's look at the show IP route connected, and let's say that we're just going to originate our loopback. So we go into the BGP process, router BGP, and in this case we are in AS 100, and we'll say network 155.144, actually 150.144. Then we have the mask keyword. So in this case, the network is not classful, where 150 would normally be a class B, which is a /16. In this case, it's not /16, so we have to explicitly configure the mask. If we were just to hit enter here, it's going to take the syntax, but it's not actually going to work. So always add the mask keyword as a general rule. Even if you don't need it, the router will just ignore it if you don't need it. But you're never going to run into problems if you always issue the mask. So in this case, the mask is /32. And then we have some other options here we'll talk about later, like setting this as a backdoor route for preferring IGP over BGP, and then route maps for setting the attributes in order to influence path selection. So next, let's look at the show IP BGP for 150.144/32. It says that I am the originator of the prefix. We can also see that the origin code is IGP because we originated it with the network statement. And we automatically copy the BGP med into the update. But in this case, the route is directly connected, so there's a metric of 0. We could see the weight value was automatically set to 32,768, and this is a local route. So let's go ahead and export our capture there and then look at what is the actual format of the NLRI origination. So we'll say monitor capture 1 export to our TFTP server, 10.0.0.100, and we'll say this is r4.bgp nlri.pcap. And it looks like the server is not running TFTP. Okay, so now we can see we have our BGP establishment or BGP updates. And specifically here, what I'm looking for should be towards the bottom, which is the update message. So an update message here was originated by router 4. And let's look into the specific network layer reachability information. Okay, so we can see that this, of course, is a BGP message. BGP message, so it's port 179. In this case, we're using source port 179, which means that router 4 is the TCP server. Router 1 is the client. Router 1 is using destination 179 is the well-known port. So had we only matched in the ACL destination 179, it would not have caught this packet. So again, you always want to match it in both directions because you don't always know by default who is the client, who's the server. Okay, the actual message in this case is an update. Inside of the update, we then have the path attributes and we have the network layer reachability information. So the NLRI is basically just the actual prefix itself. So it's saying that the prefix is 150.144 with a length of /32. And then also if we look at under the specific message, it should tell us what is the AFI and SAFI. So somewhere in here, it should say, and I don't know exactly where it is. So we have the path attributes. The origin is IGP. And also you can see here it tells you what type of attributes are these. So is it a well-known attribute? Is it an optional attribute? Is it transitive or is it non-transitive? Where in this particular case, the ones that are important, it says that the well-known transitive attribute is the AS path because everyone has to exchange that. But something that is non-transitive would be the multi-exit discriminator, which in this case is 0. Then we have the local preference. This is well known. And then we have the details of the actual message. Now, if we were to go ahead and shut this port down, so let's say we go back to router 4, and let's say we go to the loopback, and we say shutdown. Okay, this means that we're no longer going to have a route to it. So if we show IPBGP for 151.44/32, we now have to withdraw this because we don't have a match for it in the routing table. So again, the condition that must be true is that the prefix must be in the RIB, but it doesn't matter what protocol it came from. It could come from static, it could come from IGP, it could come from on-demand routing. As long as it's in the RIB as not a BGP route, then we can re-originate it with the network statement. Okay, so let's go ahead and export our capture again. And then we should see towards the end of this that router 4 generates another update, but the update message is going to be a withdraw message. So let's say, and we can see there's a lot of information here. I'm looking for, let's try this one here. Which it is. So technically, there's no difference between an update and a withdraw in BGP. It uses the actual update message, but in the NLRI, it gives you a list of routes that you should delete as opposed to adding them. So it's basically flushing the route out of the table, but when you actually look at the format of the message, it still counts as a regular update. Then it's saying the route that you need to delete is 150.144/32. Okay, the next one we have is with redistribution. So with redistribution, one of the differences here between the network statement and redistribution is the origin code. So we saw the origin code was IGP. When we use the network statement, the origin is going to be incomplete when we do redistribution. So this means from a path selection point of view, the BGP process would choose a route that came from the network statement versus redistribution first. Now, when we do redistribution, if auto summary is enabled, the process is going to summarize the routes to the classful boundary. Now, in most cases, we don't really care about this, though, because auto summary should be off on any relatively new version. But let's say maybe from a troubleshooting point of view, if they did turn auto summary on and you do redistribution, that's when it applies. So So auto summary is not for the network statement, it's only for redistribution in BGP. Now, of course, we can do manual aggregation, just the point being that it's automatic in the case of auto summary. So for example, on router 4, if we show run section BGP, and let's get rid of our network statement. So no network. And instead, let's say auto summary, and then redistribute connected. And actually, before I do this last one, I'm going to clear, let's say monitor capture 1 clear to delete the buffer, and then let's redistribute connected. So if we now show IPBGP, we see that we have 155.100 originated via us, 0000, and we should also see the 150, let me see, is the link shut down? The link is shut down. Show IPBGP, let's say pipe include 0000. So we can see that we're originating these as a classful summary. So if we show IPBGP for 151.0.0, it says the mask is /16. But again, this is not the default behavior. Normally, auto summary is off by default. So unless you specifically turn it on, or they turn it on for troubleshooting within the scope of the exam, then you don't have to really worry about this. So in most cases, you would not want to automatically summarize because you normally don't get classful networks. So you might have a /22 allegation, but you're not going to have a /16. Or even if you do have a /16, who's to say that it's from the class B space? It could be an A address that's /16, which would then auto-summarize to /8. So again, we will probably assume that this is off. But if you ever see this behavior and you're not sure why it's happening, it just means auto-summary is on. So if we show run section BGP, let's go ahead and disable auto summary. And then let's look at the show IPBGP, pipe include 0000. We can see now we're originating the actual subnets. So if we look at the details of the actual advertisements, if we show IPBGP 151.4.4/32, most of the things are the same here, but the difference now is that the origin is incomplete. So again, we'll talk about the details of best path selection later, but in general, something that has origin IGP will be preferred over something that's origin incomplete. But again, it is also setting the weight to be high, and it's setting this as a locally originated route. So if you're looking at your own origination versus someone else's, so if I redistribute a route, but you use the network statement, I will still prefer my origination. Because in general, when you do the BGP origination, you're not routing the network through BGP. It's an IGP route that you issued the network statement for, or it's an IGP route that you redistributed. So if I prefer your BGP route, it means I might possibly loop the traffic that's supposed to be internal. Now, as I mentioned, there are some other caveats to this. One is that it automatically copies the IGP metric into the BGP med, which means that there will be a difference depending on how you're doing the advertisements of the prefixes, whether the router actually chooses to use the med by default when it's advertising it to the external neighbors. So we'll see that med is a very, very finicky attribute. There are a lot of caveats with med. In most practical cases, med is not used. And the reason why is that there's a lot of disagreement between different code versions and a lot of different disagreement between vendor implementations as to how med should be actually processed. So some of them might process 0 as infinite, some of them might process 0 as best, and you can end up in unpredictable results if the code versions don't use it as a unified manner. So one of the ways that this is used in a practical case is on peering exchanges, where you have lots of routers that are peering on the same LAN segment. Then you're basically exchanging their internal metric in order to get to the external destination, and then you could look at the med based on that. But beyond that, we'll see that since there are so many caveats, normally med's not even used. If you wanted to influence inbound path selection, you would generally not use med, you would generally use AS path. Now, the other thing is that when we do redistribution from OSPF into BGP, it doesn't include the external prefixes, but again, this is a default protection mechanism. Because the idea of this is that if you redistributed BGP into OSPF, OSPF would originate it as an external route. then you redistribute OSPF back into BGP, it shouldn't take those external routes because it might have come from the BGP process to begin with. So again, it's an automatic loop prevention mechanism. Whether it actually would cause a loop or not depends on the topology. So you can disable this behavior if you want to. So under BGP, you would just say redistribute OSPF, whatever the process is, and then match internal, external in order to include the external routes. Then lastly, like we saw, it is setting the weight to 32,768. This is going to make it more preferred over someone else's origination. There is also an issue with the opposite direction. So when you are redistributing BGP into IGP, you only take the external BGP routes. This is different than the OSPF problem. That's when you're going OSPF to BGP. This is now the reverse. You take BGP, you're redistributing it into the IGP. It doesn't take the internal routes because normally those routes should already be in your IGP if you're learning them from internal. So like most of these options, you can change it if you want to. You can say BGP redistribute internal, but if you do this wrong, you can cause a routing loop. And you'll see actually if you look at this under the CLI, and if we go to the routing process and say router BGP 100 and say BGP question mark and look under redistribute internal, it tells you this is dangerous. So unless you know what you're doing, you can cause a loop and you can crash the router because either the routing table gets too big or in hardware platforms you overrun the TCAM on the actual line cards, and then if everything falls back to software switching, CPU goes up to 100% and the box just crashes. So in general, BGP to IGP redistribution and back is kind of frowned upon because of this, but we'll talk about in later cases where it's necessary, and one of the main use cases is going to be MPLS layer 3 VPNs. So if we are learning external OSPF routes and we need to send them to the MPLS provider, we would need to say match internal external for BGP. And then if for some reason we have an iBGP peering with the provider, which typically you wouldn't, but theoretically you could, then you would need to say BGP redistribute internal in order to allow these. Now the next one we have is kind of an interesting case. It's called BGP conditional advertisement, where it's the neighbor advertise map and the neighbor exist map or non-exist map. Now basically what this is saying is that I must meet certain conditions in order to originate the network advertisement or in order to not originate the network advertisement. Specifically the logic it's using, it says that we're going to match some prefix in an advertise map. Now if the prefix is true, so if the prefix does exist, then we will originate what is in the advertise map. We can also do the opposite logic of that and to say that if the prefix is not in the BGP table, then we will advertise what is in the advertise map. So it's kind of an interesting feature, and the use case for this is normally for redundancy designs, that you want to track the failure of some sort of link. If the link goes down, if it does not exist in the BGP table, then you would do an origination. So for example, if we look at our particular case on router 4, and let's look at router 4 and think about what are the different peerings that router 4 has. If we show IP-BGP summary, it has a peering to router 5 over a directly connected link, and it also has a peering to router 1. But let's say, for example, that we have multiple peerings to the external network. So let's say we have a peering to router 5 this direction, and we also have a peering to router 5 that direction. So let's go ahead and add the second one, which is going to be specifically over 155.105 and vice versa. So let's say router BGP 100, neighbor 155.105 is in AS 200. And then the same thing on the reverse direction. So router BGP 200, we're peering with 155.104, and they are in AS 100. So on router 4, if we look at the show IP-BGP summary, we should see that we have multiple peerings to AS 200. Now, if we look at the BGP config as it stands, we're doing redistribute connected, but let's say we change this, and let's say that we're going to originate our loopback with a network statement. So we say network 150.144 with a mask of /32. If we look at this from router 5's perspective and now show IPBGP 150.144, we should see that we have multiple paths to the destination because we have multiple peerings. So we're learning one over the point-to-point link, we're learning one over the DMVPN tunnel. Now, which one it actually chooses, of course, is going to be based on the best path selection algorithm. So it looks at things like the local preference, the AS path, the MED, and so on, but eventually it's going to have to decide on one versus the other. Now, the potential issue we could run into with this, let's say that from router 4's perspective, we always want traffic to be received in this link in order to get to our loopback. So we want to apply an inbound policy to say that when traffic is received inbound, or actually I should take that back, we want to influence inbound traffic flows. So we want traffic to be received in on this link, which actually means we need to apply an outbound policy. So the outbound policy affects inbound traffic, the inbound policy affects outbound traffic. So without getting too much into detail yet with the best path selection, because we're going to talk about this, one of the ways that we could simply do this would be to do something like this on router 4, to say route map prepend, set AS path prepend 100, 100, 100. That's our AS. Then under the BGP process, we would say when we're peering with router 5 over the alternate link, so this is the link that we want to be less preferred, we're going to use the route map prepend outbound. If we then clear IPBGP out, that's going to send the new triggered update through route refresh, and router 5 should now see that the AS path changes. Okay, notice the AS path now has a length of 4. This is not going to be the best route. We now are going to choose the route that goes over the point-to-point link. So from router 5's perspective, if we were to trace 150.144, we see that it goes out the point-to-point link. Okay, this is what router 4 is purposely trying to accomplish by influencing the outbound policy, which is to say the return traffic should come this particular direction. Now, one interesting thing we run into with BGP, though, is that we ultimately have full control over how traffic leaves the network, but not necessarily how traffic returns. So what this means is that in this particular case, router 4 is doing a prepend out in this direction to add 100, 100, 100 to make router 5 return the traffic in that direction. But since this decision is out of router 4's control, there's nothing to say that router 5 could not simply do something like this, to say that under the BGP process, when I'm peering with 155.104, set the weight to high, whatever, 1,000. When we now clear IPBGP inbound and we show IPBGP for that particular prefix, even though the AS path is longer, we are administratively weighting it high locally, which means that that's going to be our best path. So in other words, you don't have absolute control over how traffic returns, but you do have absolute control over how traffic exits. So this ends up in some interesting situations where you may be trying to influence traffic flow on the internet and someone else can override your policy by doing local preference inbound or doing weight inbound or a number of other attributes. This is specifically what conditional advertisement was originally designed to solve. That we're going to track one of the transit links, and if the link goes down, then we will advertise the route out the alternate path. So let's think about it this way now. Router 5 only can choose between one path over the other because it's learning both paths. It's learning the route in from router 4's tunnel peering, and it's learning it from the point-to-point peering. But what if we were able to override the process and say, don't even advertise it that direction unless this particular direction is down? So assuming that router 5 doesn't do like a static route in order to override the policy, in that case, we should have ultimate control of the inbound flows simply because we're only advertising the route in one direction. And that's what conditional advertisement is used to solve. Now, the syntax application of this is kind of strange, so let's take a look at it in the documentation. And let's just start at the main documentation page, then down to Products iOS, Products iOS, regular iOS 15.3t, Then under documentation, we want the configuration guides. And then under IP routing, we want the BGP configuration guide. And I believe this has its own document here. A VRF aware conditional advertisement. You can see there's a lot of features in BGP. So let me just search for this condition. So it's under one of these other documents. Let's try. Let me search for it in a couple of these. Conditionally originate, and this is, which document is this? This is connecting to a service provider using external BGP. So it's kind of just a very small side note in here. It says, the following example shows how to, no, that's not it. That's conditionally originating a default. Conditional route injection, conditional aggregate routes, conditionally advertising. There we go. So this is, let's see if that is the advertise map, exist map. Yeah, so this is under just configuring a basic BGP network. So let's see if they have an example of it here, because we'll see that the syntax is kind of strange. So they're saying BGP inject map originate, exist map, no, that's conditional injection. I'll have to take a look at this later to see exactly where it is. Let's take a look at the VRF aware one. This should basically be the same thing, except we don't need to match the VRF, which they should be saying advertise map, exist map. So let's look at what they have here. In this case, we're actually going to do the opposite of this. Okay, so they're saying under the BGP process, in this case, the address family doesn't matter. In our case, this is router BGP 100. And we're conditionally advertising this out to the specific neighbor. And this is the key difference between other methods, is that this is not globally conditional like a default route. This is conditional to a particular peer. Now, in our particular case, what we're specifically trying to accomplish is to say that on router 4, I always want traffic to come in this direction. I don't want this peering to be used at all unless this particular link is down. So this means that the conditional advertisement is going to be applied this way. So from 4 to 5 on the link that we do not want to use, or more specifically the peering that we don't want to use. So we're going to say, as we advertise a route out to the neighbor 155.105, we want to do an advertise map. Okay, the advertise map, they're calling it ADV1, so let's just use that one, where ADV1 says match the address that is a prefix list. Okay, so let's get rid of those. So first we have a route map that's calling a prefix list. A prefix list ADV1 is going to match the actual route. Okay, in our case, the route is 150.144/32. That's what we're trying to conditionally advertise. Okay, then we have a second condition, which is either the exist map or the non-exist map. In our case, we want this to be a non-exist map. The non-exist map, we'll call this non-exist one, is going to say that we're going to match route map non-exist one is going to match a prefix list. We'll call this non-exist one, where we have IP prefix list non-exist one is going to permit the connected link between the neighbors. Now, there's some other potential issues we could run into with this implementation. That one of the things that they don't really make as clear in the documentation is that when you're checking either the exist or non-exist, they're talking about in the BGP rib, not in the rib. Or in other words, in the BGP table, not in the routing table. So whatever we are conditionally matching against, we need to originate this into BGP first. Now, this is more difficult based on like how the actual convergence works and how we would track whether the neighbors are there or not. So there's some other steps in the recursive logic that you could take here where I could say, I don't really know if the connected link is a good indication of whether the peering is actually up. So maybe I want to configure a static route that's tied to enhanced object tracking, and then enhanced object tracking is pinging the neighbor. We're doing something like that. So you can add application level information to this by tying it to other features. In this case, I'm going to do it based on just matching the connected link. But this will then assume in order to do that, we're going to have to shut the link down, which that might not be the case in a real-world design, where the link might be up, but connectivity is not there. And in that case, the non-exist map would not be triggered. But here I'm just going to say permit 155.100/24. So this is basically the tunnel interface. So let's see if this syntax is correct here. And also I need to add one other key statement here, which is the network statement. 155.100 mask 255.255.255.0. Okay, and actually before I do this, I need to see, is someone else already originating that route? Show IP BGP 155.100/24. No, they're not. Okay, because I need to make sure that I'm the only one originating this. Otherwise, I could learn it in another path, and then it wouldn't actually do what I want it to do. Okay, so next let's look at the show IP BGP neighbor 155.145.5 advertised routes. And we're going to say just pipe include /32. Actually, let's say the full route, 150.144/32. And then we're going to look at this both ways. So 155.105 as well. Okay, this is the correct output. So now it's saying I'm advertising it one way, I'm not advertising it the other way. To make sure this is 100% working, because there have been some bugs in this feature in the past where it doesn't correctly trigger, what you want to say is show IP BGP neighbor and then the actual address. And there should be an output here that says whether the condition is actually being met or not. In this case, it says the condition map is non-exist, the advertised map is ADV1, and the status is withdraw. This means that the configuration is correct in this case. Because what we're trying to say is that I do not want router 4 to advertise this route out this peering as long as the other peering is available. So, and actually I think I matched the wrong direction. I should have said I need to match against this link. Okay, that's the one that I'm tracking. I'm not trying to track the tunnel. So I need to reverse this. I need to say this. This needs to say 45.0. Not the tunnel one. Okay, so the conditions should still be true. Let's say show IP BGP neighbor, pipe include condition. Okay, status is withdraw. If we now look at this from router 5's point of view and show IP BGP, we should see that there's only one external path, which is via that point-to-point link that we want to use. So this means when router 5 does a trace route to the destination, it only has one way to go. It's the way that router 4 is trying to influence. Okay, now we have a failure case. So the link goes down, and we should see that the state is going to change. So on router 4, we're simply going to say, go to interface gig 145 and shut it down. And if we now look at the condition should change to say the status is advertised. Now, one of the disadvantages, though, of this feature is that it's not very quick to converge. So whether you would actually want to choose this as a valid case might not really be there. And also, this is an interesting situation we have here, that if we show IP BGP for the longer match, it says it's still installed in the table. And the reason why is if we show IP route for 155.145.0, it says we're now learning it through EIGRP. We're learning it in an alternate path. So actually, to make sure this is going to work, what I need to do is to shut the link down from both sides to make sure that the route is withdrawn. So let's do this on interface, gig 145, shut down on the other side. Now router 4 should not have a route to the destination. Okay, or in this case, it has an aggregate, a /16. And if we show IPBGP for the longer match /24, we don't have that route, which means that now the condition is not met and the status is advertise. The end result is that when router 5 does a trace, it should go the alternate way. So the path that we did not want it to prefer to begin with, we're forcing it to go this way after the failure by tracking the link that failed and then say, okay, now I can advertise it to you out the alternate path because I want that to be my inbound backup. There was a question here, can we tune the BGP to change the default timer for the RIB? This I'm actually not 100% sure about. I'm going to do some more research into this before we talk about convergence. And the reason why this is an issue is they changed the BGP code. They changed it where it used to use a BGP scanner time. The scan time's not used anymore. Now the process is event-driven, but what actually triggers this event, I'm not 100% sure, for conditional advertisement. So one other way that you could make this a little bit more accurate, because notice I had to shut the link down on both sides, which in a real design probably would not be the case. So let's say maybe this is an MPLS circuit and it goes down somewhere in the provider's cloud, but your local link stays up, but eventually the peering goes down and you're not going to be able to reach the neighbor. So what you could do to fix that would be to say, let's do an ICMP ping through IPSLA, and then we'll create a static placeholder route for it. Then conditionally track that placeholder. If the SLA fails, then the route would be withdrawn, then the BGP condition would not be met, and then we would advertise the route to the alternate peer. So there are some other interesting ways to get around the problem, but it's not really going to be fast convergence. It might be 30 seconds or so, but it's not going to be sub-second like we can do with prefix-independent convergence. So again, the goal of this then is we want to originate the NLRI, but we want to do it conditionally. So it's either way. You can say if the route exists or if the route does not exist. In this example, we did what actually was the first case here. If the prefix matched in the non-exist map does not exist, then we will advertise it. Now, the fourth way that we have is conditional route injection. Conditional route injection is basically the opposite of aggregation. So aggregation, you're saying take multiple subnets, like let's say we take 4/24 routes and we aggregate them to a single /22. Now, when we do that, we know that we're creating the shorter match and we're losing some visibility in the network. Just like originating a default route. If I give you /0, you're going to send all your traffic to me, but you might not make the best decision because you don't have overall visibility. The same is true with aggregation and BGP. So in cases where you are learning an aggregate, but maybe you want to traffic engineer based on longer match routing, that's what conditional injection is for. So it's basically saying that I'm going to match the prefix in an exist map. So match the aggregate, figure out if the aggregate is actually in the table, and if it is true, then we are going to inject longer matches based on it. Then when we actually advertise those to the other neighbors, we can do some sort of filtering to say maybe this subnet goes this way, that subnet goes that way, in order to influence the traffic back inbound. So that level of detail we'll talk about later when we go over traffic engineering based on longer match. In this case, I just want to show how do we actually do the origination of the NLRI just based on the BGP injection. And again, just like the condition map or the advertised map in the non-exist, the syntax is not very self-explanatory. So I would make sure you know where this is documented to look at their particular example. So again, under IP routing configuration, under BGP, there is let's say inject dash map. So this is under configuring a basic BGP network. Okay, they're saying create the inject map that is saying I want to originate these subnets based on learning this particular path. Then they're saying the learned path is going to be the source route. So match who gave me the route, and then also separately match what I want to originate. Okay, the key takeaway from this example is that they are setting the prefix list. Okay, this is the only other example we've seen up to this point where you are setting a prefix, not matching a prefix, because we're trying to inject it into the BGP RIP. Okay, normally you would say match the route. If it is true, then perform some operation. In this case, we're saying to set or originate the route. So first thing we need to do is to match the condition. So let's take a look at router 4, and it had an aggregate that was a /16. So somebody's doing this origination. We don't really care who it is, but we can tell based on the path that it happens to be router 8 that is pre-configured with aggregation. This is one of the attributes that's added, which is basically the aggregator. So who did the origination of the atomic aggregate? But we're now going to take this /16 and let's say we generate 2 /17s off of it, where the /17s would be 155.100/17 and 155.128.0/17. So I could then use this to say I want to split my traffic. So half of it goes this way, half of it goes the other way, because 2 17s make up a single /16. Now you could go further. I could say match 4 /18s and so on. I could make as many /32s as I want, but it's based on whatever you want to conditionally inject. Okay, so the first thing we're going to do is to say IP prefix list aggregate is 150.5.100/16 permit. Then we have the prefix list that is going to be the longer matches, which are 155.100/17 and 155.128/17. And then we are going to, I'm not 100% sure if we need to match the route source or not. Let me see if they have just an example at the end. Specifies the match condition for redistributing the source of the route. The route source is the neighbor that is configured with the neighbor remote AS. The track prefix must come from this neighbor in order for conditional injection to occur. I'm going to first try this without it to see if it works. I believe that this may be required, though. What this is saying is who is the neighbor from the route? Or where did the route come from? Not who is the next hop or not who is the router ID, but it would be this particular value. That's basically the neighbor address that we're peering with. So if we were to match this, it would be something like this, to say IP prefix list, the route source is that /32 permit. Okay, let's say the route map is going to be the inject, which is going to set IP prefix list, address prefix list, the longer matches, and the route map is to match the aggregate. Is going to say match IP address prefix list aggregate, and match IP route source prefix list route source. Then we apply this globally under the process as a BGP inject map. So the inject map's name was inject, and the exist map's name was match the aggregate. So if we then look at the show IP BGP, pipe includes /17, if it's going to work, we should see it originate these routes. So let's say clear IP BGP in, clear IP BGP out. There they are. So it definitely works this way with matching the route source as well. But let me remove it and see if we can actually do it without that. Because all other examples always show it with matching the route source as well. So if we show run section route map, and let's show the full config. Let's say show run section route map or prefix list or BGP. So we have the route map injection that says to set the longer matches. There's the actual injection. So this is saying create the route, but what's the condition? The condition is we would only inject the route if the match aggregate is true. So you can see it's a bunch of steps in order to do it. So inject those if match aggregate is true, which is saying to match the prefix list to aggregate and match the route source, and then under the BGP process, then we actually do the injection. Okay, so this is the full final config for it. But let me make one change here, which is to say do not match the route source and then clear the process. I have a feeling it's not going to work if I do this. Let's just say clear IP BGP star. So let's see, do we actually have the aggregate 155.100/16, which we do. Right now it says inaccessible. This is because we're still converging. So let's see, once one of these actually becomes the best path, then the injection should be triggered. And you can see it's slow to converge. This is normal. This is just inherent to BGP. There we go. Okay, so now we have a best route. Let's see, now do we have these /617s? No, we don't. So I think this is part of the condition. But the other thing that's important about this here is notice the route source is a /32. Okay, it has to be an exact match from who the route is coming from. So let me modify this, and then let's see. Let me double check one more time. No, they're still not in there. So match the route source, and then clear IPBGP in, clear IPBGP out. Then show IPBGP for the /17s. Okay, we can see now it's advertised, and also notice here it says it's injected from that particular path. So it's basically the opposite of an aggregate then. So instead of taking the longer matches and shortening them, we're taking a shorter match and lengthening it. And again, the reason why you would do this is for traffic engineering based on the longer match. So I'm learning an aggregate from my customer, but I want to say as I route the traffic to them, I want to split some of it this way, I want to split some of it the other way. But the issue is that you don't have control over their aggregation policy. Now, also what you would typically do if this were a real design, it would be bad practice to advertise this out onto the global internet. So you would set the injected prefixes to community no export or either community local AS. Okay, these we'll talk about later in path selection. The issue is that if you start to advertise a longer match for someone in the internet table, you can actually cause a traffic black hole. And there have been some well-known cases of that in production where, for example, an ISP in Asia black-holed YouTube for an entire day because they started advertising longer matches to their address space. And the way it stands now, without secure BGP being implemented yet, there's nothing to check this. That you can advertise whatever you want as long as someone is not filtering, and then you could start collecting the traffic based on the longer match routing. Okay, any questions up to this point on any of those four methods? So either the network statement, the redistribution, the conditional advertisement, or the conditional route injection.